Another type of intermolecular force that we're going to discuss are called London dispersion forces. London dispersion forces are often abbreviated LDFs. And this is another type of intermolecular force that's going to affect properties of compounds like their boiling points, melting points, etc. Just to break this down, the word dispersion, if you disperse something, it means spread. So when we're talking about dispersion forces, it's going to have to do with something getting spread out. London, it's named after a scientist named Fritz London who first observed and explained these properties. What we need to know, though, is a few specific facts about London dispersion forces. So first thing, they occur in all molecules. And what I mean by that, so far we've talked about hydrogen bonding and dipole-dipoles, and we said those only occur in polar molecules. London dispersion forces occur in polar and nonpolar molecules. However, their effects are more pronounced in nonpolar molecules, meaning when we look at boiling point data of nonpolar molecules, the differences that we see in those numbers will be dependent on the number of LDFs, the London dispersion forces, in those compounds. Okay. London dispersion forces are also temporary. They're not permanent like dipole forces are, because molecules that are polar are always polar, no matter where they're at. LDFs are temporary. They only exist sometimes. You'll see these often referred to as instantaneous dipoles or induced dipoles. What this essentially means is that London dispersion forces create dipoles. They create polar molecules, but only temporarily, only for a small amount of time, which is different than polar molecules, which are always, always, always polar. So, where do they come from? How do they arise? Where do LDFs form? Well, let's talk about the molecule H2. Okay? We're going to draw a space-filling model here where we have an atom of hydrogen with one proton and one electron region around it in the 1s orbital. And here's another atom of hydrogen near it. Okay? And we know there is a force of attraction here that forms this bond. What we need to talk about now is our knowledge of the electron. So we know the electron doesn't exist in specific rings. We know it exists in regions of space called orbitals. For hydrogen, it's in the 1s orbital. So we're just going to say this space represents the 1s orbital for this atom of hydrogen, and this space represents the 1s orbital for this atom of hydrogen. This region is where the electron could be at any given time. So the electron could be at the top, it could be here, it could be out here, it could be out here, it could move. It is moving, and we can't predict exactly where it's going to be. We just know that this is a region where it could exist. So now let's say the electron happens to be right here, on this side of this molecule, on this hydrogen that's on the left. Well, what's that going to do? We know that there's also another electron, which I'm going to draw in purple, on this other atom. There's another electron in here somewhere, in this atom of hydrogen. We know that electrons are negatively charged and they want to repel each other. So if this electron is on the right side here, and there's another electron on this other atom of hydrogen on the right, those electrons are going to want to be as far away from each other as possible. So essentially, this electron is going to push the other electron to the other side, because similar charges repel. Remember, the protons can't move because they're locked in the nucleus. The electrons are the only thing that can move. So if this electron gets pushed to this side, and this electron gets pushed to if this electron is on this side, and this electron gets pushed over, then we're going to temporarily have an uneven distribution of charge. We're going to temporarily have a slightly negative charge here, slightly positive here. And since this electron's over on the right, this side will be slightly negative, and this side will be slightly positive. So there will be, right here, a small intermolecular force, which we're calling a London dispersion force. It's caused by electrons being dispersed, spread apart, spread around in atoms temporarily. Remember, this only exists for a small amount of time. Because this electron, once it immediately moves to another part of the atom, this electron might move also. And then that dipole that was created is gone. So these forces only exist temporarily, only for small amounts of time. Just to refresh, we said that this is also called an induced dipole. The word induce, if you induce something, you cause it. You might have heard like a woman went into induced labor. It means the doctors caused her to go into labor by giving her some medicine, some drugs. So this electron here is causing this dipole to form because it's forcing the other electron to the right side because similar charges repel. What does this look like with some actual real drawings? Well, here we go. Here's atoms of helium. We got 2 protons here, so helium and helium, helium and helium. We can see that these electrons are, randomly spread out. But immediately, if these 2 electrons come onto one side, they're going to repel these other electrons away. So that's going to cause this distribution to look uneven. And we're going to temporarily have a dipole, which is going to cause an intermolecular force due to a London dispersion force. So, key things to know about London dispersion forces. They are present in all molecules, polar or nonpolar. So if you're ever looking at a molecule and you're trying to figure out what type of intermolecular forces it has, it always will have London dispersion forces. Okay? London dispersion forces, which we should add back here, are also the weakest type of intermolecular force. So hydrogen bonds, we learned were the strongest, then dipole-dipole, and then London dispersion forces. They have the weakest effect on molecules that have all 3 of these present. But there are some things that can affect the strength of these. Some molecules have stronger London dispersion forces than others, and that's based on 2 main properties. So what are the 2 things that affect London dispersion forces? The first one is molecule size, how big the molecule is, how big the atoms are. How big they are affects them, the London dispersion forces, directly. So if you increase the size of atoms, you are going to increase the amount of London dispersion forces. Second thing, the molecule shape. Okay? And by shape, I really mean surface area. The amount of space that the electrons have to move around in. If you increase surface area, if you spread out the molecule more, that's going to increase the London dispersion forces. The key vocab word that we need to know when we're increasing size and we're increasing surface area, this is called the polarizability of the molecule or atom. If we break this word down, it's just the ability, how good the atom or molecule is at becoming polar. If it's better at becoming polar, it's going to have stronger LDFs. If it's worse at becoming polar, it's going to have fewer LDFs. So let's break these down in more detail. Molecule size. So let's look at some data. Don't worry about the electron configurations. That's not that big of a deal. But here are the noble gases. Helium, neon, and all the way down to radon. Okay? And if we look at their boiling points, we see there's a big trend here. As we go down, the boiling point is increasing. Why? What's going on? These are all just elements that don't bond with anything else. Well, helium just has a 1s orbital. So helium, would just have 1 ring. Neon has 2 energy levels. So essentially it kind of has 2 rings. And argon has 3. And on and on and on. So what we can see is as we go down the group, these atoms are getting bigger in size. As these atoms get bigger, those electrons have more space to move. It's easier for a bigger atom to become polar. It's more polarizable. That's that vocab word we just looked at. So as this becomes more polarizable, it's easier for this molecule to have London dispersion forces. So it has increased London dispersion forces. And we know that every time you have more intermolecular forces, that's going to lead to an increase in boiling point. So that's a simple visual. Increasing molecular size clearly affects the London dispersion forces. None of these atoms have hydrogen bonds. None of them have dipoles. These are temporary induced dipoles called London dispersion forces. The other concept is molecular shape. So let's talk about two shapes, hexane versus cyclohexane. Both of these molecules are nonpolar. Hexane has the formula C6H14. Cyclohexane has the formula C6H12. If we were to draw these, cyclohexane would look like this. Carbons bonded like so. And each one of these would be bonded to two hydrogens. I'm not going to take the time to draw them all right now. Hexane would just be one long chain. Carbon, 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 until we have 6 of them, with our hydrogens branched off of these carbons. Okay? We learned that if you have increased surface area, the molecule is going to have more London dispersion forces. Another way of thinking about that, increased surface area equals more spread out molecules, less compact. Molecules that kind of take up more space. Another way of thinking about it. So which one of these molecules takes up more space? Which is more spread out? This cyclohexane molecule, these carbons all bonded here in a long line, take up way more space than these molecules. This molecule, cyclohexane, where the bonds are all kind of in a ring. So therefore, this molecule is less polarizable. So it's going to have fewer London dispersion forces. Or another way of saying that is going to have weaker London dispersion forces. Hexane, on the other hand, is more polarizable. Why? Because it has more surface area. It's a bigger molecule. There's more space. The atoms are more spread out. So the electrons there's much more space for them to move within these bonds. So therefore, this is going to have more London dispersion forces. Or another way of saying that is stronger London dispersion forces. So what to walk away with? Definitions of London dispersion forces. You need to know the two things that affect them, size and shape, and why they do, as well as understanding these key properties, that they occur in all molecules, they're temporary, recognizing this vocab, and that they are weaker compared to the other three.